Okay, so with that, like I said, my advisor was Dr. Veser, and so how we turn into methane into benzene is through a reaction called methane dehydroaromatization. I know that's a long word, but I'll take you through it. So methane is the basic component that we're focused on because it's the most abundant natural gas. Dehydro meaning to take the hydrogen off the methane, and then aromatization, making an aromatic compound, which is benzene is an aromatic compound. So the problems with this reaction though is that it's very thermodynamically unfavorable, meaning we have to have high temperatures for it to react with our catalyst. And even when it reacts with our catalyst, something that is called coking happens because of the high temperatures. Coking is just carbon solid. It's an undesirable product that we don't want. And this reaction happens within the pores of our, or the microchannel of our catalyst, which is the zeolite. I'll talk about that later. So the benefits of converting methane to benzene is that it has many uses for it in the industry. You could use it as plastics, rubber lubricants, dyes, detergents. Household uses, you can use it for glues, cleaning products, paint strippers. And benzene naturally occurs in volcanoes and forest fires, so we can't really, go in there and get that very easily. We currently get a majority of benzene from oil, and yeah. So why microwaves? Like, why do we use microwaves heating instead of conventional heating? Well, so it's microwave catalysis has been a growing field ever since the 1980s, and we like it so much because of its thermal effect. It has a very selective heating, and what I mean by that is when it's so methane is a gas and our catalyst is a solid. So what happens is when our gas doesn't react with the microwaves as well as our catalyst, so we want to keep our gas phase much colder because we don't want an undesirable side reaction to happen. Which is very beneficial because in conventional heating we heat the whole thing up, and we don't want that, and it causes coke formation, which I said is an undesirable product that we don't want. It also gives us a hot spot formation, which helps disperse the metal into small particles and spread it throughout the catalyst. However, we're still trying to understand microwave catalysis, which is also a good thing why this project is helpful. So why zeolite is part of our catalyst? So what a zeolite is silicon with aluminum oxide tetrahedral structured catalyst. It's very heterogeneous, high thermal stability, shape selective. It's a porous material, as I said before, and the reaction actually happens inside these pores, and it helps shape the products. The cons that we have is that it is a small pore size, which can result in coke formation because of poor reacting product transport within the crystal. So the focus of the overall project was to vary parameters of the catalyst to improve our understanding of what makes these catalysts efficient for microwave catalysis for this reaction for MDA. And so with our zeolite, or our main component of our catalyst, it's based on the size and mesoporosity and the silicon to aluminum ratio. And then with our metal, it's for metal dispersion, speciation, metal loading, and the types of metal. So going into more depth and categorizing them more, they're categorized into the penetration depth, the number of dipoles, and the strength of dipoles. So the penetration depth is important because we want to be able to penetrate through the catalyst fully and through our particle, and so we can heat it up. The number of dipoles is important because the more interactions we have within our catalyst, the more our microwaves can be able to vibrate and excite these atoms within our catalyst, creating more heat, and the strength of the dipole, because we want more, our dipole to be more electronegativity electronegative and create, help our something that's called dielectric heating, which increases the microsensitivity of it. I focused on mainly the silicon to aluminum ratio and the metal speciation parameters. So here are 3 samples, each different samples and with, through 3 different syntheses. Isomorphic substitution, wet ion exchange, and core shell synthesis. I mainly focused on the isomorphic substitution, but my goal for the summer was to try to lower this silicon to aluminum ratio so we can compare with the other 2 syntheses. And the difference between each of these syntheses is that where the iron is built into the framework and how it's built in. So previous results have shown that the SAR and the metal speciation increase the microsensitivity of our catalyst. So on the 2 graphs, you see the y-axis as something that's called the loss tangent, which is just, it measures the amount of heat that can be generated between the catalyst and the microwave. And then on the x-axis is the frequency. So as you see, a lower SAR is favorable and gives us a higher loss tangent, which gives us more microwave sensitivity. And then on the right is the same thing, our isomorphic substitution gives us a higher loss tangent, gives us more microwave sensitive catalyst. So my results, so like I said, my overall goal was to try to get a catalyst that was with the silicon to aluminum ratio of 100. And I created 5 total isomorphic substitution, and then also the goal was to try to create a correlation graph that actually I could estimate our next catalyst, if our next target SAR. Sorry. However, we couldn't do this. It was just complicated because in some of our trials we would get a very high SAR, and then in others we would get very low. For example, the 70. We have 2 70s, one at 161 and one at 60. So we struggled with this a little bit. And this is what the zeolite actually looks like in real life. It's a white pure substance, and then under a scanning electron microscope to the right is what it looks like. And this is why it's very favorable, because as you can see, it's very structured, it's very well homogeneous without the whole catalyst. And so, since we couldn't get our SAR of 100, we're going to try a different approach. We're going to tune a wet ion exchange samples to previous isomorphic samples that we previously had, because it's easier to control the SAR of these. And then we're going to compare the reactivity and microwave sensitivity between these 2. And in summary, I guess the take-home message is that we can use natural gas more responsibly than it is. Instead of using imported oil to make benzene, we can use domestic natural gas, and we can create more jobs. And then this reaction, methane dehydroaromatization, is a promising route because it allows us to have a chance of creating methane into benzene. And then microwave catalysis is a promising way of heating. However, we want to have a more fundamental understanding. And then I just want to say special thanks to the Mascaro Center and Dr. Veser and my mentor, Yifan Deng. Thank you.